Okay, there we go. We are begun. Um, I'm going to have to talk a lot today because I got to get through the material. So you might have to listen to me a little bit more than usual. I won't get to stop as much. And the trade-off is that this is the last time you're required to hear me lecture, right? Next time will be the test, right? And I already mentioned last time, right, that the answers for that test review, the solutions for that test review are already posted, right? So so that's been there for a while. And also there is, since today's the last lecture day, there is a video posted of some of the selected problems from that test 3 sample. So the solutions are completely posted, but there's a video that I made this weekend that is shows just a discussion of some of those solutions, not all of them, but some of them. So some of the key problems from that sample test. So if you want to look at that video, if you feel like you need it, in addition to just the written solutions, you can look at that, right? That is on the Blackboard page. I think it's under class notes and videos. So it's not where yeah, there it is. All right. So the solutions are under the sample test folder, but this video is under the class notes and videos folder, right? If you want to look at that. Now, what has also been posted is since we're getting also close to the final exam, right? Today's the last lecture, and then next time will be the last regular class period. There is also posted a final exam review for those people who are going to be required to take the final exam. Some of you may be able to skip the final exam if you've got enough flux dollars, right? But many of you, most of you, will have to take the final exam. So the final exam review, there is a final exam review posted. Now, this does not have full solutions, though. It's got answers. So at the back of this review are the answers to all the problems, but they're just short answers, right? It's just the final answer. There's not complete solutions to all of the written solutions to all of the problems, but that is posted under sample test, right? Now, the schedule for the final exam is got a little bit messed up, but it's okay. So we have our test 3 on Wednesday, so that will be in the usual format, right? So you will come, either at 10 o'clock if based on the last letter of your the first letter of your last name, right? Or you will come at 11:15, right, to take that test number 3. Now, I will, of course, grade those and post the grades in WebAssign, but and then the solutions to test number 3 will be posted in on Blackboard, right, as usual. Now, the actual final exam is scheduled to be, but I had read this wrong, was scheduled to be May the 9th, which is the following Monday, during the regular class time. So I thought it was May the 11th, so which is a better time since that gives us a full week. So I reserved the classroom here on May the 11th, so you can come on May the 11th at the regular class time to take the final exam. Okay, so Wednesday, May the 11th, regular class time, take the final exam. Actually, it starts at 9:45, so you can come at 9:45 on Wednesday to take the final exam. Now, however, if you just insist on taking it on Monday, then because that was the scheduled period, you can come and take it Monday. Okay, so you can come here on Monday, because on Monday here, as an option, we will have during what was supposed to be the regular exam period, we will have a final exam review. All right, so We'll have a final exam review here from 10 to noon, going over going over selected problems, not all of them, but selected problems from the final exam review. Right. And so, but that's optional, so you do not have to come to that. I'm going to put that on Zoom, so so you can also attend via Zoom, and I will tape that Zoom session. All right, but then it wouldn't be available till Monday afternoon, the afternoon of Monday, May the 9th, right? So does everyone sort of understand how the schedule is going to work? Yeah. Lecture. Yeah, that's right. So today's the last time you'll sign the roll sheet. Of course, you have to come for the test, right? Okay. So now it's really important that you come for the test, right? Okay. So if you don't come for the test on Wednesday, that's going to create issues. So that will force me to replace your third test with the final exam. All right. Okay. So so try to be here on Wednesday, but if something comes up, right, then be sure that you contact me immediately, right? Okay, because we're not going to have a chance for a makeup, because I've got to post the answers to test number 3 really quickly so that people will have those to prepare for the final exam. And then I'll of course also post the grades as soon as I get them. Now, so Christopher asked about the flux dollars. So when will we know the flux dollars? So Christopher, as soon as I get the test number 3 graded, right? Okay, then I will send an email saying that that the test number 3 is graded, and then that's when your flux dollar total should be correct in terms of if you want to place out of the final. Now on Wednesday, Christopher, I will I'll bring with me a sheet that you can fill out for spending the flux dollars, and then, but you don't have to fill it out on Wednesday because you won't have the information, right? But you would then bring that back to me for the final exam, right? Okay. Or if you're going to be able to place out of the final exam, you can email that to me. All right. So you can scan it and email it to me, or take a picture of it and email it to me, that form, right? So you got that, Christopher, on how that's going to work? Okay, right. So there will be a sheet, and I'll give it to you on Wednesday, because everyone will be here live on Wednesday, right? So I can give you that sheet that you can then return, or if you can, even if you're testing out the final, you can bring it to me also physically on the final exam period. It's just that force you to come to campus, so you can also email it back to me. Okay, now that does create a little bit of an issue with the last two homeworks. So there's a homework that's due tonight, okay? And then be sure that you complete these homeworks by the due date, okay? Even if you're not going to take the final exam, make sure that you finish these 2 homeworks by their due date, which is, yeah, that's the 11th. Where have I done with that? Yeah, that's here. Okay. So yeah, so finish these 2 homeworks, right? Of course, especially if you're taking the final exam, because those subjects are going to be on the final exam. But of course, even if you're out of the final exam, you want to complete those 2 homeworks so your homework average will stay high, right? Because that's going to contribute to your flux dollars. But you don't have to finish them before the 11th. But you can turn your form in early. We'll just anticipate that you will finish those so that you will have whatever you're anticipating for flux dollars for the homework. Remember, if your homework exam is above a certain amount, but I forgot what it was, it's on the syllabus. Is it 88 or is it 90? You get 15 flux dollars, and then if it's like if your homework average is about 82, you get 10 flux dollars. That's from the final exam. I mean, from the syllabus, to see what those thresholds were. I changed those sometimes, so I can't remember what I put this semester. Okay, other questions about how things are going to go down here? All right, for the end of the semester. Seems complicated, but it's really not. Just prepare for the test on Wednesday. You can still use your survival cards, right, on Wednesday, and then also on the final exam, right? You can bring a survival card. Okay, so that all stays the same. I think, however, for the final exam, since we have a limited time frame, we're going to have to all come at the same time. So I don't think we're going to be able to do that in shifts. All right. So so we will have to be in the classroom simultaneously on the day of the final exam. Yeah, I got your email, Mohammed. You're celebrating Eid al-Fitr, right? So I got that. Okay. All right. So anything else that you guys want to bring up? So be sure to finish this homework. I think we've discussed this one already in class. Is there anything else on that one that was causing issues yet? So be sure to do that and then prepare really well for test number 3. So you'll have a really high score. I think test number 3 is not that difficult. So, but I may be misjudging it. So I don't want to give you the wrong impression. It's going to be problems like the homework problems or problems like the test review problems. If you're finding those difficult, then I guess test number 3 would be difficult. So really prepare for that. But I don't think the problems on the test are unnecessarily complicated, is what I'm saying on test number 3. Okay. Groovy. Well, then let's go back to our last topic and see if we can finish that. Right. And so you can finish that homework and be prepared also for the final exam. So remember, we're talking about polar coordinates, which is an alternative way, right, for representing points on a 2-dimensional surface, although you can also use polar coordinates in 3-dimensional space as well. You can also use rectangular coordinates in 3-dimensional space. And the ideas work very similarly in 3 dimensions as they do in 2 dimensions, but we're only dealing with 2 dimensions here, right? So so let's remind ourselves, this is another example from the notes, but we can use this example to remind ourselves a little bit of how polar coordinates work, right? And the idea is very simple. It's just as simple as it is for rectangular coordinates. It's just a different idea for locating a point in 2-dimensional space. So here we have the point given in polar coordinates. You can sort of tell that's given in polar coordinates, right? Because in polar coordinates, the second coordinate, remember, is an angle, right? Okay, this first coordinate is a distance. The second coordinate is an angle. And of course, pi over 3 looks like an angle measure, right? Although that's just a real number. So this could be rectangular coordinates, but it's not. This is polar coordinates. And so we want to plot that point in polar coordinates, and then we want to write down 2 other polar coordinate representations for the same point. That's one of the things that's a little bit different about polar coordinates as opposed to rectangular coordinates is the same point can be expressed with different coordinates in polar coordinates, and that doesn't happen in rectangular coordinates. So what I'm saying is once we plot this point, let's see if we can write down 2 other sets of polar coordinates that give us the same point, right? That mean the same point as this point 2 and pi over 3. All right, so remember now the way polar coordinates works. Again, the idea is very simple, right? You're going to draw on your 2-dimensional surface, right? We usually draw it horizontally, but I guess you don't have to draw it horizontally. You're going to draw half of a number line, right? Okay, only half of a number line, though. You know, usually in rectangular coordinates, well, always in rectangular coordinates, right? You draw a full number line. But in rectangular coordinates, we really only have to draw half of a number line starting at 0. I didn't label this as 0, but this is 0 on the number line, right? Okay, and that's called the polar axis. And now the way you use that polar axis, right, to represent a point in polar coordinates is as follows, right? This second coordinate, right, tells you the angle, right, formed by that point and your polar axis. So what I mean here is that this point 2 and pi over 3, it's going to lie on a line that forms an angle of size pi over 3, right, with the polar axis. So if you sort of draw the angle pi over 3, right, what does that look like? Well, how much is that in degrees? That's 60 degrees, right? So that's up like this, right? If we draw it there, kind of roughly. And I'm drawing on this, this paper that has a rectangular grid on it, which is very convenient for rectangular coordinates, but it's not so convenient for polar coordinates. You can find a polar coordinate graphing paper that is designed for more easily plotting points in polar coordinates. But I'll show you that. I'll show you what that looks like in just a moment here when we start actually pointing polar curves. But for now, we're just sort of stuck with this rectangular grid graphing paper. So there's the angle pi over 3. And so we know that this point lies somewhere on this line, okay? It lies somewhere on this line. But of course, there are lots of points that fall on this line, right? So exactly where is that point 2 pi over 3? Well, that first number tells you the distance that the point is away from the pole, right? This, the beginning of your polar axis is called the pole, all right? And so you know your point lies at 2 units away from the pole, okay? And now this is where it gets kind of hard to plot the point accurately, because you're going to have to try to figure out where on this line is distance 2 away from the pole, right? So you just have to sort of eyeball it here. Let's see, here is 2 units away from the pole, right? If we go horizontally, by the way we've marked off our polar axis, right, we can see 2 units away from the pole. So if you sort of project that up onto this line, where would that put you? Maybe about right here? Does this distance and this distance look about the same? I hope so, okay? So so there's my best guess for where this point is going to be located, right? Okay, so you can see in rectangular coordinates that's somewhere in the first quadrant, right? Now we're fixing to learn how to convert polar coordinates to rectangular coordinates, so we could figure out what this point's representation looks like in rectangular coordinates. We'll do that here in just a second. But before I do that, I want to again illustrate this sort of inconvenient fact about polar coordinates, which is this point in polar coordinates has more than one way of writing down its coordinates. So one way of writing down the coordinates for this point is 2 and pi over 3, but we can write the same point down in different ways using polar coordinates. One way would, let's see, we just formed the angle pi over 3, right? But we could get back to this same location in the first quadrant, right, by adding on a full revolution there, couldn't we? So so instead of using just the angle pi over 3, we could use the angle pi over 3 plus 1 full revolution, and that would give us the same point, right? Because that would bring us to the same line, right, in the first quadrant, the 60-degree line, right, in the first quadrant. And then as long as this distance is the same, you'd get back to the same point, right? So so here's another way of writing down the same point. It would be 2 and then pi over 3 plus 2 pi. How much is 7 pi over 3? So so see, there's representation exactly the same point. Well, you could do that a lot, right? So you could add another 2 pi, right? Okay, you could add another 2 pi here. That would give you another so add just one more revolution here. So you could write 2 and what's that, 13 pi over 3 if I add another 2 pi there. So you see there's the third way of writing down that point. Or you could draw your angle, you could write your angle, you could measure your angle in the negative direction, right? So instead of rotating in the positive direction, you could rotate in the negative direction, right? Like this. How big is that angle? Yeah, it's 5 pi over 3, but it's negative, Robbie, right? Okay, because we're going in the clockwise direction. So another way of writing this down would be 2 and minus 5 pi over 3. Okay. Now, let me show you one other way You can also change this first coordinate, okay? You can't change it too much, but you can also change this first coordinate. You could make this first coordinate negative, all right? You could make this first coordinate negative. Now, if the first coordinate is negative, where where do I locate points with negative R values there? Remember, this first coordinate is usually referred to as R. Well, let's experiment with that a little bit. So where is -2 and pi over 3? See, we were plotting 2 and pi over 3. So where would -2 and pi over 3 be? How would we interpret that negative? How would we interpret that negative distance there? Well, all right. So pi over 3, right? We drew that angle, so that brings us to this dotted line, right? Okay. If you go in the positive direction too, right, you're going to go in the direction of the angle. All right. So that would bring us to this point, right? But if the first coordinate is negative, you're going to go in the direction opposite of the angle. So instead of going out this line we would go backwards to here, down this direction. Does that make sense? Intuitively, at least. Okay. So there is the point, -2 and pi over. Okay. See, I went along this same line, except I extended the line this direction, and then I went distance 2. All right. So, how could I get this point using a negative first coordinate? If I wanted to write this point, but with a negative first coordinate, I write down. Well, look, how big is, it's hard to draw it in here. How big is this angle? This angle. See the angle that I just drew? So starting at the polar axis and going to here, how big is that angle? Extend the polar axis there. Maybe you can figure the measure of that angle better. So if I start at the polar axis and go to here, right, how big is that angle? Well, look, you're already going half of a turn. How much is half of a turn? Yeah, 180 in radians, that's what? Pi, right? But Robbie, we're going a little bit past the pi, right? How far past the pi? Remember, this dashed line is part of this dashed line, right? So how big is this? Pi over 3, right? So you're going to go pi plus another pi over 3, right? Okay. So that would be 4 pi over 3, correct? So it looks like I can use an angle of 4 pi over 3. But if you kept this as positive, see, if you had +2 and 4 pi over 3, that would bring you to this point. Okay. But if you have a -2, then you would go not in the direction of the angle 4 pi over 3. This is the direction of the angle 4 pi over 3. It would go backwards. So if you go backwards to, it brings you back here, right, to the original point that we plotted. So here's yet another way of writing this same point. -2 and 4 pi over 3 brings you to the same location as 2 and +2 and pi over. Emil, does that make any sense? Okay, all right. So you often think of this first coordinate as being a distance, which is fine, right? But we can also give it a negative value. We normally don't think of negatives as being distance, right? We don't think of distance as being negative, but in this context, we can think as being negative. You just have to make sure that we're interpreting that negative value properly. All right. Now, Sometimes it's easy to think about polar coordinates, to think about them, to convert them to rectangular coordinates, because you're much more familiar with rectangular coordinates than you are with polar coordinates. So let's practice doing that a little bit, and also vice versa as well, converting rectangular coordinates to polar coordinates. All right, let's start with this one. So 4 and 2 pi over 3. So there's a point that's given in rectangular, I'm sorry, in polar coordinates. See, the second coordinate is an angle there, right? That's kind of the tip off there, that this is polar coordinates. And we want to convert this back to rectangular coordinates. Now, first, where is that point in polar coordinates? Well, the angle is going to be 2 pi over 3, right? So you draw the angle 2 pi over 3, that's 120 degrees. So here's the angle 2 pi over 3, right? And then you go out along that angle, right? You would go out distance of 4. So I think it's right here. So there's the point, 4 and 2 pi over 3. So what quadrant is that in rectangular coordinates? Polar coordinates really don't have quadrants, but in rectangular coordinates, where is that? What quadrant is that point in? Yeah, that's the second. So you know when you convert this, Evan, to rectangular coordinates, right? Okay. The x is going to be what sign? And the y is going to be positive, right? Okay. So that gives us a little bit of clue of what to expect here when we convert this to rectangular coordinates, right? Remember, if you were trying to plot the point -4 and 2 pi over 3, where would you end up at? Again, you would go an angle of 2 pi over 3, right? But the negative would put you not along the angle, right? But in the opposite direction. So -4 and 2 pi over 3 is down here somewhere. Well, that's not the point. I just was trying to illustrate, again, the idea of having that negative r value, that negative radius value in your polar coordinates. All right, now, how do I convert this then to rectangular coordinates? Well, there are very simple formulas that we actually derived last time, so I'm not going to go back through deriving them. But here are the two formulas that you use for converting polar coordinates to rectangular coordinates, right? Okay, notice that your x coordinate is always going to be your radius value, that's your first coordinate, right? Your r value, times the cosine of the second coordinate, the angle. And the y coordinate is going to be the r value times the sine. That's easy to remember, right? Because you know cosine is always associated with the x-axis, right? And sine is always associated with the y-axis, right? So it's easy to remember that x is going to be r times the cosine of theta, y is going to be r times the sine of theta. Well, you might want to include these formulas on your survival card for your final exam, but they are easy to remember once you practice them a little bit. So those are pretty easy calculations, right? It's fairly easy to convert from rectangular coordinates to, from polar coordinates back to rectangular coordinates. Now we can also go in the opposite direction. We can convert polar coordinates, we can convert rectangular coordinates to polar coordinates. That's a little bit harder. So that takes a little bit more work. But polar to rectangular is pretty easy. All right, well, let's see then, according to these formulas, right? What's the x coordinate supposed to be here? That's going to be your r value, which here is 4, right? Times the cosine of your angle, which is in this case 2 pi over 3. So you get 4 times 2 pi over 3. Great, 2 pi over 3 is a special angle, so I can do these calculations exactly. I'm going to get 4 times, wow, what is the cosine of 2 pi over 3? Is that -1/2? I think so, right? Okay. The cosine of 2 pi over 3 is going to be the same as the cosine of pi over 3. The reference angle is pi over 3. Cosine of pi over 3 is 1/2, but we're in the second quadrant, right? So we know that the sign is going to be negative, right? Cosine is negative in the second quadrant. So I get what? An x coordinate of -2? Perfect. And that's perfect, Evan, right? Because we're in the second coordinate. We're in the second quadrant. What about the y here? That's 4 times the sine of 2 pi over 3. So we get 4 times, and now we just have to remember what the sine of 2 pi over 3 is, right? Well, that's a little bit tougher, isn't it? The sine of 2 pi over 3 is the same as the sine of pi over 3, except we may have to adjust the sign, right? What's the sine of pi over 3? Isn't that is that square root of 3 over 2, or is that also square root of 3 over 2? No, I think it's square root of 3 over 2, right? Yeah. Again, sine of 2 pi over 3 is the same as the sine of pi over 3, which is square root of 3 over 2, but you have to adjust the sign, right? But here you're in the second quadrant, so you know the sign is positive for sine. So you don't have to do anything here. So what do you get? 2 times the square root of 3? Yeah. Which is approximately, I think, about 3.4, about, okay? But that the exact value is 2 times the square root of 3. So there's our point in rectangular coordinates, -2 and 2 times the square root of 3. Did I get that almost in the right spot? Let's see. Did I get the -2 right? No. I'm too far over. Here's -2, right? I didn't draw the angle very well. There's -2. If you look at my grid lines, there's -2. And 2 times the square root of 3 is about 3.4, I think. And I'm not up far enough either, right? 1, 2, 3. I should be a little bit higher in the second quadrant, but not too bad, since I was just kind of eyeballing the location of 4 and 2 pi over 3. Let's try another one like that now. Okay, so let's try this one. 2 and minus pi over 4. Oh my God, where is 2 and minus pi over 4? Let's try plotting that a little bit. So the angle is minus pi over 4. So where does that put me? Quadrant wise? When you draw this angle? Down in this quadrant, right? Down in the fourth quadrant, minus pi over 4 down here somewhere, right? Yeah, minus pi over 4 is in the fourth quadrant. And then we have to go distance 2 out there, right, along this angle. So maybe about right here. Remember, if this were -2, you would go opposite of this angle, right? So you would go back into the second quadrant. But fortunately, our first coordinate is positive there. So we have a point somewhere that right there. Let's see if we can write it in. Let's see if we can write that in rectangular coordinates. So what's the x going to be again in rectangular coordinates? Got to remember these formulas. So what? 2 times the cosine of minus pi over 4, right? And that's 2 times. So what's the cosine of pi over 4? Don't worry about the negative. What's the cosine of pi over 4? Yeah, square root of 2 over 2, right? And then we may have to adjust the sign, correct? But because we're in the fourth quadrant. But in the fourth quadrant, cosine is still positive. So you don't have to, the sign is still positive, right? So the cosine of minus pi over 4 is square root of 2 over 2. So what do we get? Square root of 2 here? That's it, right? Because the 2's cancel. So we get square root of 2. And for the y coordinate, you're going to get 2 times the sine of minus pi over 4, which is only slightly different, right? Because the sine of minus pi over 4 is going to be minus the square root of 2 over 2. You know, sine and cosine of pi over 4 are square root of 2 over 2, but since we're in the fourth quadrant, sign will be negative. So we know that this sign is minus the square root of 2 over 2. So we get minus the square root of 2. Easy, right? So this point in rectangular coordinates is square root of 2 and minus square root of 2. That's about 1.4 is the square root of 2, right? So it's about 1.4 and minus 1.4 is where it's located there. And rectangular coordinates. I didn't do so bad here. Got a little bit too far, I think, down when I was plotting that in polar coordinates. All right, you guys try this one because this is a pretty basic. This is a pretty basic polar coordinate problem. So we'll surely have this on the test. Just taking this is polar coordinates though, okay, right? Polar coordinates and converting them to rectangular coordinates. So that looks like rectangular coordinates, right? If you didn't know better, you would think that was rectangular coordinates, but it's not, it's polar coordinates. So use these formulas again, but you'll have to have your calculator because you have to compute the sine and cosine of 4, but 4 is not a special angle. So you'll need your calculator here. But remember, this is radians. So make sure your calculator is in radian mode. Don't do the sine and cosine of 4 degrees, right? It's the sine or cosine of 4 radians. Try that for me. See what you get. Try it. Okay, so let's try this. This shouldn't take too long, right? This is just arithmetic with your calculator. So the x coordinate is going to be the -3, keep the negative, all right, times, and then the cosine of 4. So you just have to see what your calculator tells you the cosine of 4 is, right? Okay, and then multiply that by, be sure you multiply it by -3. So be careful about the sign. What does that turn out to? What now? Altogether, what? After you've done all the arithmetic, it's about 1.96. Is that what, did y'all, someone else get that? 1.96? Okay, Fernando. All right, Fernando says 1.96. And then what about the y coordinate there? So that's -3 times the sine of 4. And that's probably quite a bit different, but what now? 2.27. Did y'all get the same thing? 2.27? Anyone else get that? All right, so we're at about positive 1.96 and positive 2.27. Oh, so we end up in the first quadrant. That's not much fun. Okay, so end up in the first quadrant there. 1.96. Very close to 2, right, on the x-axis. And then on the y-axis, just a little bit above 2. Let me erase this so I can plot that point. So apparently that point is very close to 2, 1.96, right? And then it's a little bit above 2 on the y-axis, maybe about right there. So in polar coordinates, there is -3 and 4. Does that make sense? That -3 and 4 should be there in polar coordinates? I mean, because the rectangular coordinate is supposed to be 1.96 and 2.27, so it's supposed to be about right there. Let's try plotting that in the original polar coordinates. It's very easy in rectangular coordinates, right? But let's think about it in the original polar coordinates. So you have to think about how big the angle 4 is, right? So convert that to degrees because we're not going to be able to figure that out without converting it to degrees, right? How big is 4 converted to degrees? Multiply by 180 and divide by pi. Like that. 229.18. So 229.18. If you draw 229.18 that brings you into the third quadrant, right? Because it's past 180, but it's 49 degrees past 180, right? So it brings you close to a 45-degree line here, right? In the third quadrant. So apparently 4 radians looks something like this, right? Okay, that's about 229 degrees, I think. But remember, we're going a negative radius, right? A negative R value. So you're not going to plot the point along the angle. You're going to go backwards, right? And when you go backwards, where does that put you at? Well, apparently right there. Okay, so yeah, that sort of matches up. Okay, that makes me a little bit more confident of these calculations. Let's try another one, but now let's make it harder. Okay, so let's take 2 and -2 and see if we can convert that to back to polar coordinates. Now, here are the formulas for converting back to polar coordinates. They're not as much fun, okay, as converting from polar to rectangular. You know, to go in polar coordinates, right, you need to have the R value and you need to have the angle. The R value is easy to compute, okay, because this comes from the distance formula. We showed this last time. So remember, this is for going from rectangular to polar. So the R value is just the square root of the sums of the squares of your 2 rectangular coordinates. So it's the square root of x squared plus y squared. That looks like the Pythagorean theorem, right? That's exactly where that comes from. That's nothing more than the Pythagorean theorem. So in disguise. So there's how you compute the R. That's the easy part. The theta is the hard part, right? Trying to find the proper angle. So to find the proper angle, take the quotient of your 2 rectangular coordinates, y divided by x, not x divided by y, but y divided by x. And then you have to compute the inverse tangent, all right? So you will probably need your calculator, right? Unless it's a very easy value. You'll probably need your calculator to compute theta. Make sure you keep your calculator in radian mode, though, because when we're writing down polar coordinates, we always give the second coordinate in radian mode. All right, I mean in radians, not in degrees. So, well, let's try this then. So let's plot this point first, though, in rectangular coordinates. So 2 and -2 is right here, correct? So you can easily figure out, no, maybe not easily, but I think you can pretty easily, Amanda, figure out what an angle to use, right? If you want to put this in polar coordinates, what angle can we use? Well, think about it there. I mean, that's a 45-degree angle, right? So if you want to, you can measure the angle in the positive direction. So that would give you, what's that angle in the positive direction? No, in radians.
Oh, I just don't know.
Yeah, you know this, right? Because you know this angle is pi over 4, right? Yeah, this angle is yeah, but the reference angle is pi over 4. So if you were going to draw the angle in the positive direction, it would be going all the way around, except you would be missing just pi over 4. 3 pi over 4 would be in the second quadrant. 7 pi over 4. Yeah, okay. Remember, all the way around is 8 pi. I mean, it's 2 pi, right? Which is 8 pi over 4. So yeah, so 7 pi over 4 is a possibility. But you also said, Amanda, why not just make our lives easy and measure the angle in the negative direction? And that would be minus pi over 4. So we could also put minus pi over 4 here, see, as the angle measure. And again, see, that just points out what we mentioned earlier, right? In polar coordinates, you can write the same point lots of different ways, right? Now, what about the R value, though? Okay, so what's that distance from the pole down here? Well, now you really do have to use this formula, right? Okay, so let's see. Square root of 8, yeah, which is 2 times the square root of 2. So So you're right, Emil. It's going to be r is going to be the square root of what is it? 2 squared plus minus 2 squared, right? And so you get square root of 8, which you can simplify if you want to as 2 times the square root of 2, but even you can leave it as square root of 8 as well. That's approximately what, 2.8, but the exact value is 2 times the square root of 2 or square root of 8. You can leave it as square root of 8. That would be okay. So there it is. There it is written in a couple of ways in polar form. Now, however, we were able to look at this. We were able to look at this point and figure out what the proper angle is supposed to be. But let's use the formula and get the angle. So according to the formula, theta is going to be the inverse tangent of y divided by x. So that's what, minus 2 over 2. So that's the inverse tangent of minus 1. And then you have to remember what the inverse tangent of minus 1 is going to be. Your calculator will tell you what? Negative 0.79, which 0.79 here? 0, so this is minus 0.79, right? Okay, which is minus pi over 4. If you put that in radians, that's minus pi over 4. So notice the calculator gave us this answer, 2 squared root of 2, and then minus pi over. Okay. If you but you can figure this out exactly. You would have to think of minus 1. I want the inverse tangent of minus 1. So let's drop the minus sign for a moment and just think of the inverse tangent of 1. Well, what angle has tangent 1? That's pi over 4. Okay, so we know the reference angle is pi over 4, but we need a negative tangent. So where is tangent negative? Well, it's negative in the second quadrant, right, and in the fourth quadrant. Okay, all right, negative in the second quadrant and the fourth quadrant. But this point is definitely in the fourth quadrant, right? So we want an angle in the fourth quadrant here. Oh, so minus pi over 4, right, would do it, or 5 pi over, or 7 pi over 4 would do it as well. So a little bit harder, right, to convert from rectangular coordinates to polar coordinates because you have to deal with inverse tangent. The calculator makes it easy, but if you want exact values, it's hard because you have to think of the inverse tangent exactly. Yeah. Oh, the signature sheet. Yeah. All right. Last time here. We better try another one. So we sort of get this idea down. But you'll definitely need your calculator here, right? Because we're going to compute the inverse tangent here using the calculator for sure. All right, in radian mode. So what about the point minus 3 and 5? So where is minus 3 and 5? Let's see. Minus 3 on the x-axis, 5 on the y-axis. So up here, right, there's the point in rec. Is that 5? Nope, missed, didn't I? Go up a little bit more. 1, 2, 3, 4, 5 up here. Okay, so there's the point in minus 3, 5 in rectangular coordinates. Let's see what that point looks like in polar coordinates. All right, so I'll calculate that. Then we got to calculate the r. That's pretty easy, right? And then just use your calculator to compute what the theta is going to be using your inverse tangent button, right, on your calculator. I'll try that for me and tell me what these two coordinates are. The r coordinate you can give me exactly, but the theta, right, you're going to have to give me in decimal approximation. So so we're going to end up with an approximate coordinates no matter what, I think. So these two formulas, right? Those are the key ones that you want to remember for your homework and then for the final exam. So you may have to put those into your on your survival card. Remember, this is converting from rectangular to polar, right? Did y'all get something for R? Square root of 34? I'll buy that. Did someone get that at home? Square root of 34 as the R value. Can't simplify square root of 34 at all by hand. 34 is 2 times 17. Can't break down 2 and you can't break down the 17, and either one of those things are perfect squares. So there we have it. Square root of 34 is just square root of 34. We can write down what it is, what its approximate value is. That would be 5.7 or something like that, maybe. 5 point what? 5.83. Okay. And but now for the theta, you're going to have to definitely give me the approximate value, right? Remember, you get the 34 by just squaring these two coordinates and adding them together, right? And then taking the square root. So minus 3 squared is 9, 5 squared is 25, 9 plus 25, definitely 34, right? So we get square root of 34. What about for second one there? Yeah, Robbie, he's engrossed by this problem. Okay, so what about the theta? So inverse tangent of something, right? Put it up here. Theta is going to be the inverse tangent of this, right? 5 over minus 3. And what does your calculator tell you is the inverse tangent of 5 over minus 3? Someone get that? Chatters?
Negative 1.03.
Minus 1.03? Sounds good to me. So there we have a negative angle. That's fine. See what my calculator says. Whoops, I'm in degree mode. Darn it. I messed up. Okay, so I'll have to trust y'all on this, right? Okay. Minus 1.0. Radian. Hard to check that though, right? Okay, because to check that, you would kind of want to scribble a graph of this point, right? But this is in polar coordinates, so it's really hard to easily graph that point in polar coordinates, right? You have to think about, well, how much is square root of 34, and then how big is that angle, right? Okay, so not easy just to quickly double check that, right, to see if that is correct. What about this one? Minus 5 and minus 1. So again, so easy to plot that, right? In, rectangular coordinates. So maybe about right there. I wonder what that looks like in polar form, right? So what about the R value? Just take these two and square them, right? Add them together, so you get minus 5 squared plus minus 1 squared. That looks like, and then the square root of that. So that looks like the square root of 26 to me. Again, can't simplify that by hand. Square root of 26 is 2 times 13, and neither one of those is perfect squares. So just leave it like that. And what about now then our angle? So it's going to be inverse tangent of minus 1 divided by minus 5. That's pretty easy, right? That's the inverse tangent of 1/5, inverse tangent of 0.2. My calculator says also about 0.2. So what I got? 0.197. So so square root of 6 and about 0.2. If I round that off a little bit, right? That. Does that make sense? May have stumbled here on we may have stumbled here on an issue with on an issue here with converting from polar to I'm sorry, from rectangular to polar. All right, so I may have neglected this issue. Where is this? If you plot this point, square root of 26 and 0.2, right, then where does that really put you? Well, let's think about that. Square root of 26 is a little bit more than 5, right? What is that? About, is that 5.1? About 5.1, right? Okay. And what about 0.2 radians, though? What is that in degrees? Well, remember, how do you convert from radians to degrees?
11.5.
Right, times 180 and then divided by pi. So what does that give us about in degrees? What? 11.3. Oh, 11.3 degrees. So if you actually graph 11, let's see, 11.3 degrees is maybe like this, right? Ooh, so 0.2 radians looks about like this, about, that's roughly 11 point, roughly there, 11.3 degrees. So if you plot this point, you're going to end up, unfortunately, where? In the first quadrant, right? But -5 and -1 is actually, you can see that's in what? That's really in the third quadrant. So what happened there in our conversion? Well, we're on the wrong side of the angle, right? Okay. This point, -5, -1, really should be in this direction rather than this direction, right? So how can, oh, so we need to fix that. Okay. We need to fix that. We need to fix that by fixing the angle. The distance is fine. Okay. The square root of 26 is the right distance away from the pole, but the angle is off. So instead of going into the first quadrant, right, we really want to get into the third quadrant to this point. How can we do that? Well, you could change this value, right? How could you change this value so that instead of going into the first quadrant, we go in the right direction into the third quadrant? Because this point, -5, -1, is really in the third quadrant. How can you change? You can change this. Instead of making that positive square root of 26, what can you do there? Make it negative, right? So instead of moving in this direction along the angle 0.2, we would go in the opposite direction. So you can fix this by changing this to a minus square root of 26. That would work and get you in the correct quadrant. Or you can change the angle. So instead of having this angle of 0.2, we really want this bigger angle that comes all the way like this, right? So what would that be? Well, what's this reference angle going to be then? Look at the picture, right? If this is 0.2, then this reference angle would also be 0.2, right? But notice you are 0.2 past 180 degrees, right? So take the 0.2 and add on an extra 180 degrees. So you could keep the sign positive if you want to keep your radius positive, and just take your angle and add on 180 degrees. What's 180 degrees in radians though? Pi. So just add on here a pi. Okay. That would get you also right spot. Oh, okay. So I know the mistake I had I know why this problem came up. This formula, theta equal the inverse tangent, that may not give you exactly the correct angle in your polar representation. It gives you the reference angle. So you may have to look at the picture and adjust this angle appropriately to make sure you're in right quadrant. Okay. So when you use these two formulas to write down your polar representation for your rectangular coordinate point, make sure you check that, okay, a little bit to make sure that you're in the right quadrant. You may have to adjust the theta appropriately. Hopefully that issue doesn't come up too much, okay? So when you use this formula, you get the correct reference angle, but you may not actually get the correct angle to put into your polar coordinates. Well, I said this was going to be a little bit trickier, right? Okay, so there it is. All right, now notice what I've copied here is this table. This table is really familiar to you, right? That's just the sine, cosine, and the tangent. But what we're really interested, I think, mostly here are the sine and cosine for the special angles, correct? Well, you're really familiar with this table. The reason I've got that copied, though, again, is because now we're going to start looking at not just plotting points in polar coordinates, but also plotting curves in polar coordinates, because you can create curves in polar coordinates just like you create curves in rectangular coordinates. All right. So how do you create curves in rectangular coordinates? Well, you write down equations involving x and y, right? So you write down equations involving x and y, and then you look for solutions to those equations, right? And plot the solutions to that equation. Usually you get lots of solutions, right, to that equation. And when you plot all those solutions, you get some sort of curve, okay? Well, same thing works in polar coordinates as well. In polar coordinates, you can write down equations involving, instead of x and y, you can write down equations that involve r and theta, all right? And then when you find solutions to those equations, those will be points in polar coordinates. Plot those points, you'll get a curve, okay? In polar coordinates, just like when you plot solutions to equations in rectangular coordinates, you get a curve. Now, as you might expect, though, polar coordinate curves and rectangular coordinate curves, they're curves, but we can plot a much different variety of curves in polar coordinates than what we get in rectangular coordinates. I'm going to demonstrate some of those for you here in just a second. First, though, let's try something very simple. Let's take this, or relatively simple. Let's take this curve in this equation in rectangular coordinates, and let's turn it into a formula in polar coordinates. Let me show you what this curve looks like, by the way, in rectangular coordinates. Y squared equal 4 times x. So I've got a graph of this, I think, already created. There it is. All right. So there's the graph of y squared equal 4 times x. Okay. So when you graph that, you get this curve. That's just a parabola, by the way, but notice it's turned sideways. So you get this sideways opening parabola. So it's not a very complicated curve here in rectangular coordinates. By the way, notice that is not a function. That curve in rectangular coordinates is not a function, right? Not a function because there's an x value that has 2 different matching y values, right? So definitely not a function, but it is a nice curve. Okay. All right. Now let's see what that curve looks like when I convert that to polar coordinates. So I'm going to get an equation now in polar coordinates that involves r and theta instead of x and y, because you know in polar coordinates that's what we label the two coordinates, right? The r coordinate and the theta coordinate. All right, so what does this equation look like in polar coordinates? All right, so man, let's see if we can figure this out. Well, let's see. Do you remember how to do you remember y in remember this formula, right? Okay, that y is equal to r times the sine of theta. So in that equation where we saw the y, we can replace that with r times sine of theta. And then we won't have y variable, or we'll have r's and thetas, right? Which is what we need in polar coordinates. And same thing for x, right? Remember this equation for converting from polar coordinates to rectangular coordinates. X is r times the cosine of theta. That means where I have x in this equation, I can replace it by r times the cosine of theta. So let's do that. And let's see what it's going to look like. It's probably going to be a little bit messy to start with, right? But let's see what we get. So when I have y, I'm going to replace that with r times the sine of theta. And then when I have x, I'm going to replace that by r times the cosine of theta. And really, there you have it. It's already done. There's an equation now, still an equation, right? There's an equation in polar coordinates because it involves theta and it involves r instead of x's and y's. However, I'm going to simplify this a little bit because frequently when we write down equations, or almost always, not just frequently, almost always when we write down equations in polar coordinates, we like to have them solved for the variable r on one side. We do that often with rectangular as well, right? Because when you're writing down equations in rectangular coordinates, you often like to have it written as what? Y equal to something, right? Okay. This one is not written in that form, but frequently we like to write our rectangular curves in the form y equal to, some formula involving x, right? Same thing, same idea happens in polar coordinates. We like to rewrite the formula so that we have not theta, but r equal to, and then some formula involving theta. So we like to solve the equation for r in other words. Ooh, this doesn't look too easy to do, right? I want to try to solve this equation for r. Oh, by the way, this is that was squared. I forgot that was squared. Okay, well, so let's see if we can take this equation and solve it for r. All right, when you square this, you get what? R squared sine squared theta, right? Both these things are going to get squared, is equal to 4r times the cosine of theta. Now, I'm going to divide both sides here by r. Because that gives me r times sine squared theta is equal to 4 times the cosine of theta. See, that's looking a little bit better, right? Because remember, I want to take this equation and solve it for r. I want to get r on the left-hand side is equal to, and then some formula on the right-hand side, okay? So just divided both sides by r here. So I get r times sine squared theta equal 4 times the cosine of theta. And now, well, how can you finish solving that for r then? So how can you isolate the r? Yeah, divide both sides by sine squared theta, right? So that's what I'm going to do here. I'm going to divide both sides by sine squared of theta. So again, how did I know what I was trying to do here? So how did I know to take these steps? I was trying to solve the equation for r. Now, the right-hand side here is what looks kind of messy, right? So I get 4 cosine of theta divided by sine squared theta. Now, actually, I've already finished what I wanted to do because notice on the right-hand side, you have a formula involving theta. That's what I wanted, right? Here I have a formula involving theta. So in a sense, I'm done. Here's this formula in polar form. But I'm going to simplify the right-hand side a little bit because I'm going to show you something here. Let's break that sine squared theta into two parts. So I'm going to write it as cosine theta over sine theta times 1 over sine theta. Is that the same thing that I started with? I don't want to change this. Well, what's cosine theta times 1? That's cosine theta, right? And then notice in the bottom you have sine theta times sine theta, which is sine squared theta. Why did I bother to break it up like this? Why was that helpful? Well, because in trig, things have lots of different names, right? What's cosine theta over sine theta better known as? Almost tangent. You're close. Sine theta over cosine theta is tangent, not inverse tangent. But like the inverse tangent, cotangent. Yeah, we didn't use that too much, right? Okay, but there it is. Cosine theta over sine theta is cotangent, not inverse tangent. That's something. What's 1 over sine theta? That has another name as well. Almost. Nope, not inverse sine. Cosecant, right? Yeah, okay. One, yeah. Emil, 1 over the cosine is the secant. 1 over the sine is the cosecant. Yeah, right. It's been a while. So, so there we have it. There is the there's how I was trying to write the formula. It's 4 times the cotangent of theta times the cosecant of theta. Okay. And all of this is equal to r. So there's your, let me write it again up here. So there's your formula, this equation written in polar form. Which do you think is easier? Probably the rectangular is easier, right? Okay. But there are going to be instances now where the polar is much easier than the rectangular. This is not one of them. Okay. All right. But there will be plenty of curves where writing the formula for the curve in polar form is easier than writing the formula for the curve in rectangular. And that's one reason why polar coordinates are useful to us. Let's graph this now in polar form. So Desmos is really good at graphing in both rectangular, and it can graph rectangular equations, and it can also graph polar equations really well. You may wonder, of course, the r you just type in is r. If you want to know how to get the theta, just type in the word theta in English, which is theta. So type out the spelling for theta, and Desmos will replace that by the Greek letter theta. Okay, so there's 4 cotangent theta, cosecant of theta. Let's graph that. So I'm going to turn this one off and turn this one on, and look what you get. The same picture, right? Okay, the same curve. Okay, it was supposed to be the same curve. It's just the equation is in polar coordinates rather than rectangular. Now, notice that what's interesting here, though, is Desmos has given you a domain here. Okay, so Desmos gives you the option of what do you want as the domain of theta? What theta values do you want to use in this equation? And here it's limited from just one full revolution, 0 to 2 pi. Okay. If you up that to 4 pi, I think you're going to, let's try changing this to 4 pi. You're not going to see any difference in the, you're not going to see any difference in the picture here. If I can get this to respond. I don't think you're going to see any difference in the picture there. There we go. Yeah. Because if you go to 4 pi, that's just making another revolution of theta, right? So you're just plotting the same points over and over again on this curve. So you get exactly the same picture. Wow. Let's test this. Here's what I mean by testing it. Let's do some hand calculations here. So let's check and see if a point really is on this curve. So to get points on this curve, right, you have to find solutions to this equation. You have to find solutions to this equation. You find solutions to this equation just like you do in rectangular coordinates. Pick a value for r or theta, and then find what the other variable, what the other matching variable is. Here, it's much easier to pick the theta. Okay, all right, much easier to pick the theta, and then use the formula to compute what the matching r is. All right, and then let's see where that point actually ends up. All right, so you guys want to pick a value for theta for me? This is an angle, so what's your favorite angle here? 45. So let's let theta be pi over 4. Okay, let theta be pi over 4. And now we're going to plug pi over 4 into this formula, right? And see what the matching r value turns out to be. Okay. I think it'd be easier to do this with a calculator, but your calculator may not have cotangent and cosecant on them, right? Remember, right? But that's okay, because what's the cotangent the same as? It's the same as cosine over sine, right? And what's the cosecant the same as? It's the same as 1 over the sine, right? So don't forget, these identities can help you do these calculations. Actually, I might be able to do this by hand. So I get, if I plug pi over 4 in for theta into this formula, what am I going to get? I'm going to get 4 times, what's the cosine of pi over 4? You pick this one, Emil. So what's the cosine of pi over 4? Square root of 2 over 2. So you get square root of 2 over 2 here divided by, what's the sine of pi over 4? Same. Square root of 2 over 2, right? So this first set of parentheses is just going to reduce to what? 1, right? What about the second set of parentheses, the cosecant? That's 1 over the sine. But what's the sine of pi over 4 again? Yeah, square root of 2 over 2. When you divide that into 1, you're going to take the reciprocal. So instead of getting here square root of 2 over 2, you'll get 2 divided by the square root of 2. See, you get you just get the reciprocal. Okay. So what does all this work out to be? This is 4 times 1 times 2 over the square root of 2. So that looks to me like 8 over the square root of 2. Can you do that with your calculators now? What's 8 divided by square root of 2 approximately? You know, do that. 8 divided by square root of 2. Someone do that for me. Maybe 5.65, 5.7 about. Okay. Oh, so our R value there turns out to be 5.7. Right? Oh, so there is a point that's on the curve. Okay. But remember, this is in polar coordinates. So when the R is 5.7, right, and the theta is pi/4, there's a point that's on that curve. Okay. So if you plot that point in polar coordinates, that point should be on the curve. Let's go back to our graph here. See if we can find that point, 5.7 and pi/4. Now look, unfortunately, I've got this thing set up in a grid, right? But I'm going to change this to another style here of grid. Okay, this is a polar grid. All right, see why this is easier to look at? Okay, because in polar grid you have the angles plotted, right? And then you have these distances away from the pole. So it's much easier to locate points, polar points on this grid than it is on the rectangular grid. So what point were we looking for? Pi/4. So that's this angle, right? Pi/4, and then out how far, Emil? Okay, so let's count out 5.7. So this is 1, there's 2. So here's 3, here's 4. So there's 5 right there, see? And then 5.7, well, apparently about right there. Wonder if that will tell me what that point is. Doggone it, Desmos. So, okay, Desmos stopped cooperating. Right. But right there is, I think it's right, okay? Pi/4 and 5.7. Notice that falls right on that curve. I thought this was coordinates, but this was. Cool, right? Okay. So there's one point on that curve. Of course, how do you get all the other points on that curve? We just found one. How do you get all the other ones? Yeah, you have to put more angles, right? It's just tedious like it is in rectangular coordinates, right? You have to come in here and you have to fill in more angles, right? Okay. This is what Desmos was trying to indicate with the domain here. It was like, how many angles do you want me to fill in? All right. Okay. Well, here we want you to fill in angles from 0 to 2 pi, right? Okay. From 0 to 4 pi. 0 to 2 pi would have given exactly the same curve as well. Ooh, that seems terrible, right? Well, it kind of is when you're doing it by hand. All right, so it's not pleasant when you're doing it by hand, but fortunately, we won't be doing it by hand a lot. Okay, we'll rely on the calculator or the computer to help us with making these graphs. All right. Now, all right, let's take a brief break here, and then we're going to come back and let's try taking these curves and putting them back in rectangular coordinates. So these curves are in polar coordinates. Can you tell that, right? Because you have R and theta, right? So those curves are in polar coordinates. You want to convert them back to rectangular coordinates. So if you plot R equal 5 secant theta, wonder what sort of picture you're going to get, and then what does that same curve look like in rectangular coordinates? I think I have this one, so let's see what picture we are going to get. Is this the? Oh, that's not the one. No, not the one. Okay, so never mind. Well, maybe if we're able to convert that back to rectangular coordinates, we'll be able to figure out without having to graph it what sort of picture we're going to get from that polar curve. All right, so let's stop right there for a moment. We'll come back at about 11:35 and then try converting these to rectangular curves that were much more comfortable. let's resume here and let's talk some more about these curves in polar form. And so one thing we can do with curves in polar form to understand them a little bit better is convert them back to, try to convert the equation back to rectangular form. And sometimes that's easy to do, and sometimes that's not easy at all. So I'm just going to show you some examples of this process of taking a curve that's in polar form and then converting it back to rectangular form. Okay. You're with me at home. Everyone head up. If you want to sleep, you can go home. Okay. All right. So let's see what this is going to. Let's see what this curve it will look like if we can manage to convert that back to x and y coordinates. And again, it's not always easy to do, and so it really helps to have seen some examples, because there are sort of different things you can do at different times to convert these back to rectangular coordinates. So the examples are really helpful. So when you're working on the homework and you're asked to do this process sometimes, come back and take a look at these examples, and they may give you a clue as to sort of what steps you might want to take. So remember, we want to get rid of the r's and the thetas here and convert this back to x's and y's, right? So first thing I want to do though in this one is let's take the secant, and let's not write this as secant theta because we're not used to using secant theta that much. Okay. And so how can you rewrite secant theta? What would be the normal way of writing secant theta? 1 over cosine, right? As we mentioned though, just a moment ago. So let's write that as 1 over cosine theta, because we're usually a lot more comfortable with cosine. Okay. Now, the next thing I'm going to do here, and there's no, the only good reason for doing that is I want to get rid of this fraction. And so let's see what happens if we can get rid of the 1 over the cosine theta. So how can I get rid of 1 over cosine theta? Just to eliminate the fraction from the equation, Evan, though, what can you do? I mean, just in general, how do you get rid of fractions from equations? What trick do you do to eliminate fractions? Alexander, are you computing? Huh? What are you typing? I bet you're not typing 1 over cosine theta, because that's kind of hard to type. Yeah, take your phone and put it up. No, no, into your bag. Yeah, yeah, and zip that closed for me. Right. Okay. Yeah, this is important stuff. This is going to show up on the third test. I mean, on the final exam, right? Okay. And you need to score well on the final exam. All right. So you got a lot writing on the final exam. Right. So you need to be paying attention. All right. So do what now? Just in general, to eliminate a fraction, what do? Multiply by the denominator, right? Okay. So let's multiply there by cosine of theta. So notice there on the left-hand side, I'm going to get r times the cosine of theta, right, is equal to just 5. Now, maybe that was worthwhile or maybe not, okay, but that looks a little bit better. But what's really encouraging, though, is what I end up with here on the left-hand side, which is r times the cosine of theta. Okay? And the reason I like that is because that looks like one of my equations, right, from earlier, for converting from rectangular to polar or vice versa, right? Remember those? If I scroll all the way back up here, remember those equations? Remember this one that said r times the cosine of theta is equal to what? That's x. Oh, so see, I can replace that r times the cosine of theta Now I can replace that by x. So one thing you're looking for when you're trying to convert polar back to rectangular is expressions like this, where you have r times cosine of theta or r times sine of theta, right? Okay, because those convert directly to x or y. So r times the cosine of theta is immediately x. So that's it. Now we have just this. See, that was very simple, right? We got a little bit lucky there. Because now we have this equation that just involves x's and y's. In fact, this one just involves x. You just have x equal 5. Oh, so we know what x equal 5 looks like, right? Okay. If you graph x equal 5, what sort of picture would you get? A line. What? Yeah, you get a straight line. What kind of line, in fact? Vertical line, right? So this is just the vertical line that runs through 5 on the x-axis. Oh, so if we go through the trouble of graphing r equal 5 secant theta in polar coordinates, you're just going to get this vertical line that goes through 5, right, on the x-axis. So so here's a case where the rectangular equation, I think, is easier than the polar equation, right? The rectangular equation for that straight vertical line is just x equal 5. Very simple equation, right? But in polar coordinates, a little bit more complicated. R equal 5 secant theta. So in this case, polar coordinates kind of win the battle there, right? Of what's the easiest way to represent that curve. Okay. In rectangular coordinates, straight line, they're easy to that straight vertical line, easy to write an equation for that. In rectangular coordinates, a little bit harder in polar coordinates. But now that's not always the case, all right? And I think in this example, this kind of is going to be a win for polar coordinates, because when we figure out what this curve looks like, we're going to see, I think it's easier to express that curve in polar coordinates than in rectangular coordinates. Here's a very simple curve in a very simple equation in polar coordinates, right? You just have r equal 2 times the cosine of theta. And so let's see if we can convert that back to rectangular again, so that we sort of know what that thing looks like, right? Okay. So here's the second sort of or maybe not the second, maybe really the key trick that's useful in converting from polar to rectangular. What I'm going to do here is, and at first it seems like it's just sort of arbitrary to do this, but I'm going to square both sides here. All right, at least let me say it differently. It's kind of squaring both sides, but that's not the way I want to think of it. All right, let's take both sides and multiply by r. So at first, it looks like, you're kind of making things more complicated, right? But remember, your goal is to convert this to rectangular coordinates. And when you multiply both sides by r, you get some benefit here. Look what happens on the right-hand side. You get 2 times r times cosine of theta, right? Now, why is that helpful to you? Right, because that is something we can convert back to rectangular coordinates easy, right? So that cosine of theta was kind of a sitting duck for us, right? Because we knew when we multiplied it by r, we would get r times the cosine of theta. But in rectangular coordinates, r times cosine of theta is x, isn't it? So notice that you can convert the left-hand side here, the right-hand side, to just 2 times x. So see, that is now in rectangular coordinates. Now, good thing happens also, though, we're fortunate, also happens on the left-hand side, because we end up with r times r, which is r squared. But remember, how do you compute r when you're trying to convert between rectangular and polar coordinates? Yeah, we're doing that a moment ago. Remember, that's the square root of x squared plus y squared, right? So where you have r squared written down, that's the same as x squared plus y squared. So over here on the left-hand side, also easy to turn that back into rectangular coordinates. That's just x squared plus y squared. Oh, so there is the curve in rectangular coordinates. X squared plus y squared equals 2x. Now, I wonder what is that curve? So if you graph x squared plus y squared equal 2x, what sort of picture will we get? Let me see if I have this one. Let me see if I have this one graph. Oh, darn it. No, that's not it either. Okay, so we're on our own here. I thought I had a graph of that one, but we're just gonna have to figure this one out with pencil and paper. I think I can do this stuff. Okay. Do you have any, just from looking at the form of the equation, do you have any sort of guesses? It's a circle. What clued you off to that, Robbie? The squares, right? The fact that you had x squared plus y squared in there, that looks like an equation that could have a circle, right? It could be a circle. It could also be an ellipse, but you know, circles or ellipses are very similar, right? But actually, it's a circle. Actually, we can figure out what circle it is. Bring the 2x back over to the left-hand side. So you have x squared minus 2x plus y squared equals 0. And now guess what you're going to do with the x squared minus the 2x? Well, you want to factor, but in order to factor, what do you have to do first? You want to complete the square. Remember this? We want to complete the square on the x squared minus 2x so that we can factor this. What do you put in here to complete the square? Along with the x squared and the minus 2x. So there's another thing that's going to be on the final exam. It's not on the third test, but this will surely be on the final exam. Plus 1, right? Yeah, you put a 1 in here. Remember how you got that? Take the minus 2 divided by 2 and square that. Minus 2 divided by 2 is minus 1, squared is 1. So put a 1 in there. Don't forget, you also have to put it on this side though, right? Since you added 1 here, you have to add 1 here as well. And now how does x squared minus 2x plus 1 factor? Now we factor, Robbie. So how does x squared minus 2x plus 1 factor? I think that's x minus 1 squared, right? And y squared is the same as y minus 0 squared. Don't need to write it like that, but it helps when you're thinking of a circle. So you have y minus 0 squared, and then on the right-hand side, you have 1. So what circle is that? That is a circle. So what do we know about that circle? Where's its center? One, 0, right. So the center is at 1, 0. And what's the radius? One, right? Because 1 is the same as 1 squared, correct? Oh, so if you graph this in rectangular, I'm sorry, in polar coordinates, you're just going to get a circle. It's going to have its center at 1, 0, and the radius is going to be 1. Man, I got to convince myself of that. So let's try graphing this one. I'm going to add a graph here. All right. So what was my what was that formula? Use the keyboard here. So it was what? That's the wrong keyboard though. Try this keyboard. So no, in polar coordinates. R, what was it? Equal something. Yeah, R is equal to just 2 cosine theta. Was it 2 cosine theta? And remember to get theta in Desmos. If you're graphing in Desmos, just type the word theta. But there it goes. Ah, and so, oh, we were right. There it is. There's the circle. See? Okay. And now that center is indeed at right there at 1, 0, and the radius is 1. Okay. Huh? Yeah, well, it's just a small circle. Oh, so here's a case now where look, here's the equation in rectangular form. It's kind of messy, right? A little bit because it's got squares and so forth in it. But in polar form, it's a very easy equation for that circle, just 2 cosine theta. Okay, so there's a case where the circle written in polar form is better, is easier, gives you an easier equation than the equation written in rectangular form. Now, in astronomy, this idea works to your advantage because again, the orbits of planets are what? Elliptical, right? Okay, and it turns out it's easier to work with the equations for those ellipses in polar form than in rectangular form. Okay, so when we study the orbits of objects, right, in space, their orbits are ellipses. It's easier to work or to understand those orbits when they're written in polar form than in rectangular form. All right, let's look at this one. Now, this one I have, okay, so 2 plus 2 cosine of theta. Let's see if we can convert this back to, let's see if we can convert, this is going to take some work, all right? So let's see if we can convert this to a rectangular form. This is not going to be easy to convert to rectangular form, okay? So let me warn you, you're just going to have to, this is an example you really need to see. And sometimes it's just messy to do this. Let's take a look at what this thing looks like. Because this one, finally, I think I have it graphed. So let's see if this was, yeah, there it is, graphed in polar form. So you get a curve that looks like this. That's called a cardioid because that is a heart shape. It's supposed to be a heart-shaped curve. This is kind of the top of the heart up here, right? Okay. So it's not really completely heart-shaped, but kind of. Okay. So that's called, that kind of curve is called a cardioid. So, you know, it's kind of circular, right? Kind of elliptical. It's a closed curve, right? And so it's kind of got a formula like the one we just saw, right? One we just graphed was r equal 2 cosine theta, which turned out to be a circle, right? If you add on just extra 2, you get kind of a circular curve, but it's not quite a circle, right? It's a little bit different than a circle. But not a complicated curve, right? Let's see what that same curve looks like though in rectangular coordinates. It's going to look terrible in rectangular coordinates. So this is definitely a curve that's easier to write down in polar form than it is in rectangular form. Do y'all have any? So I want to convert back to rectangular form. And what's really useful for me to have in the equation are things like r cosine theta, or r sine theta, or r squared, because those are the things I know how to convert back to rectangular form, right? So if you look at this equation, you have any idea of how we can get some r sine thetas or r cosine thetas or r squareds or things like that in there? What now? Yeah, multiply both sides by r. That's a place to start. Okay, so let's see how that goes. So I'm going to multiply, but it's not going to be perfect here. I'm going to multiply both sides by r to start with. So that's nice. I get r squared. So I know what to do with the r squared, right? How can I convert r squared to rectangular form? That's x squared plus y squared. Yeah. So whenever you see r squared in polar form, in rectangular form, that's x squared plus y squared. So on the right-hand side, I get 2 times, see, I have to distribute r. So I get 2 times r plus 2 r cosine theta. But now the r cosine theta I like also, right? Because that's the same as what? X, right? As we saw up in the prior example. So I have x squared plus y squared is equal to 2r plus 2x. Now, because r cosine theta is x. Now, this is where things go awry. All right, so things are going swimmingly up until this point, but now things are about to get messy. Because this is not quite in rectangular form, right? Because what's still in there, unfortunately, an r, darn it, the r. So I got to get rid of the r. All right, so let me show you what you can try here to get rid of the r. You have to be, this one you have to be kind of clever about. Bring the x over to the left-hand side. So you get x squared plus y squared minus 2x is equal to 2r. And now, instead of r, what would you prefer to have here? Because remember up here, what's r squared? That's x squared plus y squared, right? Okay. So instead of having 2 times r, I'd rather have r squared. Now, you can get r squared by multiplying both sides by r, but unfortunately, that's going to leave you an r on the left-hand side still, okay? So that's not the way we're going to get rid of this r. I'm going to get rid of this r by squaring both sides. Not multiplying both sides by r, but squaring both sides. But that leaves you with a really messy thing on the left-hand side. But that's just life. Don't try to expand this product, okay? Just leave it as x squared plus y squared minus 2x squared equal to, and then what do we have on the right-hand side there? Well, that's 4r squared, right? Don't forget to square the 2 and the r. But now I'm done because what's r squared? That's x squared plus y squared. So there you have it. That's an equal mark there. There you have it. There is that cardioid, which is very easy to write down in polar form. This is what it looks like in rectangular form. Nasty, right? Who would want to graph that? Who would want to graph that equation in rectangular form? It's just terrible, right? Okay. That curve in rectangular form is the same as this curve, 2 plus 2 cosine theta in polar form. Let me show you that. So because I think I've got that one graphed. So there it is in polar form. Let me open it in rectangular form. And you'll see it's, so there it is in rectangular form. That's just what we derived, right? And notice you get exactly the same curve, okay? Same cardioid. But you would be really angry with me if I put this rectangular equation on a test and said graph it, right? Because that would be just terrible. Okay. All right. So, but that's what it comes out looking like, and much easier to work with, right? Much easier to understand in this simple polar version. Let me show you some graphs now of some other polar curves. So we were going to graph some by hand, but unfortunately we've run out of time to graph them by hand. But the process for graphing by hand in polar form is the same as it is in rectangular form, right? You have to get a table of solutions and you have to plot points, right? So how do you get a table of solutions? Well, you plug in values for theta, right? For instance, if you were graphing this equation, you would plug in values for theta and then find the matching r value and then plot those points, okay? And then try to connect them with a smooth curve. So it's the same process of graphing curves in polar coordinates as it is in rectangular coordinates. What's a little bit messy though is, of course, you have to know some trig, right? Because you have to get sines and cosines a lot. But otherwise, the idea is the same. Let me show you what some of these curves end up looking like. The ones that we were going to graph by hand. These are very simple. Like r equal 3, that is a polar equation. Notice the theta is missing, but it's still a polar equation. I wonder what that looks like when we graph it. Or theta equals pi over 3. There's another polar equation. I wonder what that looks like when we graph it. Or 2 sine theta. I think we already know what that one's going to look like when we graph it. Let's see those graphed though in polar form. So I think I've got those. Oh, cool. So here they are. Here's simple. That's about as simple polar equation as you could get. Just r equal to a constant. Notice the theta is missing, but we just have r equal to a constant. Have any idea what that's going to look like when you graph that? A straight line? Yeah, because in rectangular coordinates, you'd get a straight line, right? Yeah, but not here. Okay. There's what it looks like in you get a circle, yeah. Okay. So if you just have r equal to constant in polar coordinates, you get a circle. So circles are kind of similar to straight lines for polar coordinates. All right. Circles are a very basic shape in polar coordinates. Here's the second one. This is theta. Arctangent of y over x, remember that's the same as theta, is equal to pi over 3. So you might think that one is a straight line. I think that one is going to be a straight line. Yeah, okay. That one does turn out a straight line. Here's a simple one. R equal 2 sine theta. What do you think that one's going to come out? That's going to be a circle. Oh, there's a circle. It's a circle that's just been transformed. Well, so far, these curves are all kind of boring, but let me show you some more interesting curves in polar form. Okay. All right, so there's the one we already saw. That's the cardioid, right? Whew. Got a big set of axes there. So there's the cardioid, 2 plus 2 cosine theta. Let's see what happens, though, in polar coordinates if we move the 2. So I'm going to remove this 2, and let's move this 2 inside the parentheses. I wonder what that curve looks like. Oh, cool. All right. So you see, you can get some really nice curves in polar coordinates. You get a, that's right, a 4-leaf clover here, right? Okay. Forgot what this is called. A lemniscate, I think, is the official name for that, but you would call it a 4-leaf clover. Wonder how we get more leaves here. Any idea? I bet if you change this number, don't you think we get more leaves there? Let's try 8 there. Whew, yeah. So there you can get these multi-leaf clovers, right? That would be a really strange equation in rectangular coordinates, right? But in polar coordinates, very easy curve, just very simple formula. Yeah, it's terrible to graph that one by hand, right? Okay, so you really need to have an understanding if you were trying to graph this by hand, what sort of curve you were expecting to see, right? This one doesn't look too bad. It looks like this one, except the coefficient is less than 1. Let's see what that does. Wow, I wasn't expecting that. Okay, so that looks like some sort of spirograph there, right? Okay, notice those were almost very similar equations. You had a constant times theta, right? This is just 2/3 and this one is 8, but you get a much different curve. Very nice, elaborate curve. Yeah, right. Spirograph pattern, right? And this one I think is really going to be strange. Yeah, okay, so really shapes in polar. Okay, of course that's a much tricky equation. This one you get this really nice graph. So sometimes our polar graphs can be really nice curves, all right? That we cannot easily duplicate in rectangular. That we cannot easily duplicate in rectangular. On your homework now for this section, what you really have to remember is these formulas for converting to rectangular to polar and vice versa. So those formulas are in the notes here somewhere. If I scroll up far enough. Right here, right? Okay. Those are the formulas for converting from rectangular to polar and vice versa. This is from going from polar to rectangular in A, and for B is going from rectangular to polar. Okay, so that will be useful in the homework. And then you do have to make some graphs in the homework, but be sure that you do not want to do these by hand, okay? So use either your graphing calculator or use the tool in Desmos to make the graphs. Let me show you where you're asked for one. So like in problem 14, it says just sketch this graph. So you will just use the either your calculator to key in that formula, or use the tool here that's in Desmos that's given. If you go to the top of the homework, the link to that tool is right there. So just click on that, and all you have to do is just enter this formula in polar coordinates, right? That's just a formula that's in there as an example, but you would change that formula, right, to match the one that's in your homework. Well, what does that formula look like? You get a cardioid, but this cardioid has a little loop in the middle. Okay. Graphing that. Okay, so and then you just, of course, as usual, right? Just match those pictures up, right, with your whatever the answers there are given as possibilities. Okay, well, all right. So remember, next time is test number 3, right? So that does not cover polar coordinates, right? That only goes through the end of polynomials. And then Monday review, optional, and then next Wednesday, final exam. A review is posted for the final exam. I'll remind you of that on Wednesday. Okay, guys, finish the homework that's due tonight. There is one due tonight, so make sure you finish that. That is on the test.